So, our next speaker is Benny Avelin from University of Uppsala, and he's going to speak about cheek-square cutoff phenomena or cutoff phenomenon for Galerkin projections of Fokker Planck equations with monomial potentials. Please go ahead.
Thank you very much. And apparently now I'm a Libra, what do you say? Libra team, as it was said on the website. That's nice. Yeah, so this is kind of a long-running project that we just finished together with Gerardo Barrera. And since Gerardo was really insisting that we should have the Europe co-funded on the archive preprint, I also put the Swedish Research Council there as well. Anyway, jokes aside, let's start with some setup. So as the title says, we are interested in the cutoff phenomenon. And so let's start a little bit with the history of the question for those who don't know it, and that includes myself, because this is not really something I have been working on. This is Gerardo's field, I would say. So in the classical cutoff, which is basically this situation here, it started with Alduin Diaconis, where you look at shuffling of a deck of cards. And basically, if you look at the convergence in total variation of a shuffle, of how far away you are of doing 1, 2, 3 shuffles, and you have to, of course, define what you mean by a shuffle here, then the distance sort of basically stays constant for a while, and then it sort of abruptly sort of transitions to being quite well mixed. And there's sort of this kind of funny slogan, which is sort of 7 shuffles is enough, which is from this paper. And basically what sort of happens in this situation is that if you look at the size of the state space of, say, a finite Markov chain, then this convergence becomes more and more abrupt in a sense. So basically one can think of a picture that kind of looks like this. So you're sort of staying very close to having distance 1 in total variation, and then there's a certain sort of transition time, which is the cutoff time, when after that it sort of abruptly converges to something which is pretty close to being sort of distance 0. So that's sort of the traditional topic where you look at the size of the state space as sort of the complexity parameter of interest. And then later, or I would say much later, Barrera and Jara studied the basically small noise perturbation of an ODE system, or an ODE, I guess is the first paper, and then an ODE system is the second one. So it's basically when the noise level goes down, the system sort of slows down, but you have the sort of similar kind of behavior in total variation that for a time which depends on the noise level, there is a certain sort of cutoff time when the convergence will become quite rapid, I would say. So there's some kind of abrupt convergence type of thing there. So this is sort of the classical is with state space. The sort of Barrera-Jara version is when you look at the size of the noise, which is precisely the sort of regime that we will be in, which will look at the size of the noise. And sort of quite very recently, Bordenave and Mathien also looked at cutoff with respect to if you have a system with initial data that becomes more and more localized, you might see cutoff in basically in certain systems on hyperbolic manifolds. That's, I think, the only paper I've seen that are interested in localized initial data. And all of these methods, they sort of rely on, or they are about the total variation distance. But there is one paper by Chen and Salaf-Kost from 2008 where they look at L2. And then they give a spectral criteria for cutoff, which is basically that the first eigenvalue, which is the lambda 1 here, and this is the cutoff time. And here you have n, you can have n or epsilon or any sort of complexity parameter. And if this goes to infinity, then there is cutoff in L2. And it's basically you prove it by inserting the definition of cutoff into the spectral representation of the distance. So this is sort of what is has been done. And what we have been interested in is sort of, can you see this kind of cutoff phenomenon in the spectrum of the generator in some sense? And what in the spectrum actually determines the cutoff time? Okay, so what kind of model are we interested in? Well, as the title suggests, we are interested in monomials. So we are interested in a stochastic differential equation in one dimension that evolves sort of a gradient type. So you have your minus of some potential, derivative of potential. And this potential is given by this kind of this monomial. So the prototype is when gamma is 1, then this is just x squared, and then you get the Ornstein-Uhlenbeck process. But here you can have gamma to be bigger than 1, and also less than 1. And there's a kind of weird threshold phenomenon, or sort of a critical case is when gamma is precisely 0. And then you get just the absolute value of x. So that's the potential. And then we look at the initial data. So we say that we take the process starts sampled from some initial data. The initial data is just a localized bump around x0. So here you have x0, and this is just normalized to be a probability measure. And the width of this sort of interval depends on epsilon. So this is delta of epsilon, or actually 2 delta of epsilon. So we will take delta to be going to 0 as epsilon goes to 0. So this is kind of what you would call localized initial density or peaked initial density. So it sort of covers two sort of aspects. One is you have vanishing noise, but you also have a peaked initial data. So that sort of covers two kind of phenomenons that together gives rise to cutoff in our case. And the invariant measure here is just the Boltzmann density. So it's just some normalizing constant, and then you have e to the minus v over epsilon here, which is this. Okay. So in order to describe anything here, we have to talk a little bit about the spectrum, because we will look at the distance, which is sort of Galerkin distance. So the process has a generator which is given by this one. So you have the epsilon, which is the noise level, and then you have the second derivative u, and then you just have the drift term appearing here. This is where the monomial enters, and the dual of that is just the equation for the density then. So the density evolves according to the dual. And in our case, for the monomial potential, we have a discrete spectrum. And since it's 1D, it's actually all the eigenvalues will be simple. So you have the first one will be 0 because constants solve this equation, or actually the constant 1, which will be the first eigenfunction. And then there's a spectral gap, which is given precisely by the distance between this lambda 0 and lambda 1. And then you have the rest of the spectrum following that. And with this, you get an orthonormal basis of eigenfunctions. We call them psi k epsilon, and they are a basis in this weighted L2 space. So you have to weight it with respect to the Boltzmann measure. And since this operator is self-adjoint, things behave very nicely, and you can sort of transition between the spaces where the density lives and the space where the sort of the observables will live, like expectations of the process, for instance. And the transformation is precisely given by this, and this is called conjugation, basically. So you just take the density you're interested in, you subtract the stationary density, and you divide by the stationary density. And then you get something that will evolve with the semigroup generated by this generator. So that means you can sort of, you only need to know the spectrum of the generator to say something about the convergence to equilibrium through these eigens expansions. So you don't have to do anything fancy here. So that's the setup. And now we can define the distance. Okay, so we have the first item here is the projector. So this is just the projector. So what it does is that it takes input as a function f, and then just projects it onto the n first eigen or eigenfunctions. So this projects the function f to the space spanned by the n+1 first eigenfunctions. So remember, we have a 0 eigenfunction, which is the constant eigenfunction. And this dot product is always taken with respect to the L2 with the weight. So this is the Boltzmann weight. So if one is in this situation, we can define what we call the truncated chi-square distance. So this is it's this distance. So what you're basically looking at is you project the ratio of the density with respect to the stationary density to the first n+1 eigenvalues, subtract 1 because this oh shit sorry, my hands did something. Okay, so the density rho epsilon t will converge to rho epsilon infinity. So this ratio will go to 1 in this. I'm sort of pointing at my screen, and I realize you can't see what I'm pointing at, so I have to use the pointer. So this ratio will go to 1, so then this projection will be projected onto the first eigenfunction, which is just a constant 1. So then this will converge to 1, and then subtract 1, so this will converge to 0 as time goes to infinity. And the weight is now the Boltzmann weight here. And if you use precisely this eigen expansion up here, and you can just rewrite the distance in this way because of the linearity of the equation. So what you end up with is these pieces, which are the coefficients. And then you have these weights. So this is the exponential weights. You have the eigenvalues here, lambda k epsilon, and you have the time. there. And then you have this coefficient here. So that basically you can sort of see how this, how each term corresponds to or sort of contributes to the distance here. So unlike the sort of Wasserstein or total variation, you can sort of see precisely how each mode here contributes or how each oscillation here contributes. And you might wonder why we're looking at the truncated distance. And it is simply because first of all, we did it because we couldn't do it for the full distance. But when we started to calculate on it, we realized that it's actually interesting in its own right because it gives rise to a phenomenon that we'll see, which is sort of the main result, which is sort of kind of a weird threshold phenomenon that appears that you would not see in the full distance. I think, I'm not sure, but you still see it here in the truncated distance. Okay, so once you have that set up, we can talk about really what we're trying to prove or what is cutoff. And we will adapt the definition a little bit from the standard definition because it doesn't really fit precisely, but it's close enough. In spirit, it's the same. So what is cutoff in the most classical sense, or the simplest definition of cutoff, is that if you are at the cutoff time, so this is think about this picture, and you multiply the cutoff time by a constant which is, say, between 0 and 1. So then you are a little bit to the left. So here, this is c less than 1. You're a little bit to the left of the cutoff time. And the way you have cutoff, if as the complexity parameter, so this is epsilon going to 0, as the complexity parameter evolves, you will converge to 1, or sort of in total variation, it would be 1. In the L2 distance, it's infinity because that's the diameter of the L2 space. It's infinity. So that means that if you're just slightly below the cutoff time, you will, if the complexity parameter is really small, you're very, very far away from having converged. While if the constant c here is just above 1, then you're to the right of the cutoff time, c bigger than 1 here. And then as the complexity parameter is evolving, you're then really close to being converged. So this is the weakest notion of cutoff. So if you're at the cutoff time, the distance to equilibrium will always be something like, say, 1. If you're a little bit to the left, eventually you will be infinitely far away from equilibrium. And if you're a little bit to the other side, you will be basically at equilibrium when the complexity parameter evolves. So a sharper version of this is the window cutoff. So then you introduce a window and then also so you can look at here's the window. So if you are at the cutoff time and you basically deviate with an r on the scale of the window, you will get something that depends non-trivially on the r as the epsilon goes to 0. So you get something in the limit for different limits for different r's, basically. This is a bit stronger notion. You need that the window should be small with respect to the cutoff time. So that's why you have w epsilon over t epsilon goes to 0. And the strongest notion of cutoff is the profile cutoff. And it basically says that this particular limit converges to a particular function, which is called the profile function. So it's sort of when you're zooming in close to this cutoff time and you zoom with the correct scale, you will get some non-trivial profile appearing. And when you have, say, profile cutoff and you look at the mixing time here, you get some kind of expansion of the mixing time in terms of the profile. So the level of the mixing level, eta, you can parameterize the mixing time by the cutoff time, and then this profile function of eta times the window. And then you only make an error of the size of the little o of the window. So this is the definition, and the way this differs from the traditional classical definition of cutoff is, first of all, that this is infinity. So otherwise, if you look at total variation, you would go to 1, because if you think about it as a diameter of the space, that is the correct thing to put there. And the other thing that we do not require is that the mixing time or the cutoff time goes to infinity as the complexity parameter evolves. In most other cases in total variation, if the mixing time will go to infinity, but it turns out it won't in our setting. Okay, so let's dig deep and go to the main results. So recall, we have a monomial potential. We have a distance, which is given in this Galerkin sort of cutoff, or sort of this truncated chi-squared Galerkin distance. And if you start with initial data, which is not at 0, and gamma is bigger than 1, you will never get cut off. And the reason for that is that all eigenfunctions are uniformly bounded. And this is a bound which is uniform with respect to epsilon. So it doesn't depend on epsilon, the upper bound. What that means is that you can never have, this distance can never go to infinity. So that's why you will not have cutoff when gamma is bigger than 1. So then it's the peculiar thing that happens is that if you really look at, you try to calculate cutoff when gamma is less than 1, you notice that there are certain things that happens. For instance, when gamma is between 1/3 and 1, it's a different kind of scenario than if it's less than 1/3. And we will see a little bit, well, I'll try to explain why that is later when we look at how the eigenfunctions usually behave and how the eigenfunctions have a different behavior when gamma is less than 1/3. But in this case, if gamma is bigger than 1/3, you have window cutoff, and the cutoff time, you can define it by basically using this is called the relaxation time. And in many situations, the relaxation time is the cutoff time, but not always. In this case, it is. So basically, you just use the first eigenvalue, or lambda1, the first non-zero eigenvalue, to determine what should be the time. So this only depends on the first one. And the window is precisely is this quantity, which maybe you could guess if you look at the scaling of the equation. We are not able to prove profile cutoff. I would imagine there is profile cutoff, but it's difficult to prove that it's there, basically. And So that's the case when gamma is bigger than 1/3, and then when gamma is less than 1/3, another thing happens. You get actually profile cutoff, and the mixing time is now determined by the largest eigenvalue that you have in your truncated distance. And the profile is given precisely by that largest eigenvalue. And here, lambda n, this is the when epsilon, so lambda n is lambda n 1. So it's when epsilon is 1. So it's kind of weird that when gamma is between 1/3 and 1, you use the relaxation time. And then when you look at the estimates, it turns out that all the terms in the sum of the distance have the same size with respect to epsilon. So at the cutoff time, they are all of these terms in the sum are non-zero uniformly with respect to epsilon. But when gamma is less than 1/3, the largest eigenvalue will dominate. So then when you are at this cutoff time and you let epsilon go to 0, eventually you will only see this term, the lambda n term in the sum, and all the other terms in the sum will just disappear. And the kind of peculiar thing that happens as well is that the mixing time is 0.1 as epsilon goes to 0. Which is kind of, but I guess it's kind of surprising to some extent. Okay, so this is when x0 is not at 0. And when it's at 0, you have a little bit of a different setup, and you have to be a bit more careful, because when you are at 0, you have to care about the parity of the eigenfunction. So if you have, so that you recall the initial data is just a uniform distribution on a box. And if you're centered at 0 and your eigenfunction is, say, odd, that was not supposed to pass through the origin, but if it's odd, then the integral with rho x naught epsilon against psi k epsilon, this is then always 0. So you only care about the even modes when you are at 0. And specifically, what you realize when you do the calculations is that you have to take the even mode, which has the highest index when you're at 0. So En here is just all the indices that corresponds to eigenfunctions which are even. So this is another way to characterize the even eigenfunctions in this case because of symmetry. Here psi j is just psi j1. And not only that, you also get a profile cutoff. And the profile is given precisely by eta minus lambda m, where m is the index of the highest surviving even mode. The window is the same as before. And that's what you get. And if you compare this to so this is when gamma is between 1/3 and 1. There's a similar statement when you are below 1/3. But when gamma is 1, which is the Ornstein-Uhlenbeck case, you don't see this kind of cutoff at 0. So if you have 0, x naught 0 in Ornstein-Uhlenbeck case, you get no cutoff. While if x naught 0, you get profile cutoff. And this you can calculate by hands because the eigenfunctions are explicit, the Hermite polynomials in this case. Yep. So that is the main results. And to us, it was kind of surprising that you have this sort of threshold phenomenon appearing, and the fact that you can get cutoff at 0 is not something we expected at all when we first did the calculations with Ornstein-Uhlenbeck case, where you see that you shouldn't see that. The same kind of phenomenon appears if you look at these. If you look at the Ornstein-Uhlenbeck and you have the total variation distance, you will not get cutoff when you start at 0, and you will get cutoff if you start away from 0. So how does the proof go, or what do you really need to do when you estimate the mixing time? Because all in all we have to do, or all the technical difficulties of this paper is to calculate the mixing time. And in order to calculate the mixing time, if you think about the distance squared is this sum, you have these coefficients, which is given here. And these are localized, so this function is like it's just a localized density around x naught. So what it basically boils down to is to calculate the coefficients, and not only that, you also need to calculate. In order to calculate the coefficients, if you see them as the rho epsilon 0 is just an integral sort of close to x naught, you basically need the pointwise value of the eigenfunction close to x naught. So you need this piece. So you need to know, how does the eigenfunction grow at x naught as epsilon goes to 0? And since these eigenfunctions are not polynomials or anything, they're just some strange exponentials, it's unclear a priori how they actually behave as epsilon goes to 0. So you need to do some more detailed and sort of fine analysis of the eigenfunctions in order to figure this out. So the entire proof is based on trying to get the pointwise size of the eigenfunctions as epsilon goes to 0. So how do you basically do that? You basically start, so this step we already explained. So you apply this scaling, and because the potential is this monomial, so v of x was just x to the 1 plus gamma over 1 plus gamma. So this monomial is scaling invariant if you scale correctly. So you can transform, if you take precisely the power epsilon to the minus 1 over 1 plus gamma, you can transform L epsilon to L1. And this also gives you how the eigenvalues depend on epsilon. Okay? If you do this transformation, you'll see that in order to know what happens if you put here x naught, and you put there x naught, you see that if u epsilon is an eigenfunction of L epsilon, then and u is an eigenfunction of L1, then in order to know the pointwise value of u epsilon x naught, you need to know the asymptotics of the eigenfunction of L1. So that's sort of so we need, that's what we need. So that gives us step 3. So the epsilon dependence of this psi k epsilon is converted into large X growth of the problem for the fixed operator L1. So this is when the noise level has size 1. So how do we do that? Well, we basically transform this equation, the generator, to a Schrödinger type equation. It's called in high dimension, it would be called the Witten Laplacian. And then we basically run a WKB type expansion. It's not exactly the same because we're doing it for an operator which is L1, which has no epsilon left in it. So in order to do the WKB expansion, you have to introduce a formal parameter. You do the same thing as in the classical case, but it turns out that that's the right thing to do anyway. In the sense that for a monomial, you can do the WKB expansion up to a certain point, and then it turns out that the remainder term you get in the expansion is in fact uniformly bounded. So you get that the expansion is valid up to a multiplicative constant. So in the sense, well, the WKB expansion is pointwise true, but you can estimate it up to a multiplicative constant.
Benny, sorry.
Yeah.
May I ask a question? Can you say a little bit more about these WKB expansions? It's my first time hearing about this, please.
Oh, yes. So basically you make an, well, I have it here. Okay. So basically it's this. So you take like a Schrödinger equation of this form. So it's like a W prime prime, and then you just have some potential. Now we have a very specific potential, but we don't have to care about really the form of it. You make an ansatz like this. And actually what you really need to do is to make an ansatz, which is like eta to the n, no, to the I, sorry. Eta to the I in front of here. And then you plug this v into the equation. You match the exponents of eta. And then you get a different equation for each eta. And that leaves you with, like, you get an equation for the first term, you get an equation for the second term, and then you get like a hierarchy of equations. That looks like this. So once you've solved the first one, you can solve the second one, and you can solve the third one. So you can keep going recursively and keep solving them. And then in the end, you have to take care of what's left, which is then the remainder term, which will solve an equation of the same type. And it's down here. It's quite horrible.
Thank you.
Yeah. So that's what you have to do. But if you do, yeah.
Sorry, Benny.
Yeah.
Can I ask you also a question about this
Sure.
WKB? Typically, these WKB expansions are only asymptotically convergent, not
Yes.
convergent series. Is it like this also in this case?
Here you have to stop at a finite
Okay.
n, yeah. And you can, so the way this works is that you can expand it to any finite n, but there is a certain value of n, depending on gamma, for which everything that's left is just bounded.
Okay.
Yeah. So you basically just try to figure out where you should stop. You run it until that's true. Of course, one of the main things in the paper is to prove that it's actually bounded. So you have, yeah. So that's actually something that we couldn't really find in the literature. We had to do it because, as you say, it's always it's often it doesn't really work rigorously. It's sort of only somehow it's just heuristics in many cases, but in this case, it actually does work.
Okay, I see.
Yeah.
Thank you.
Yeah, no problem. It's a good question.
But perhaps I would ask one follow-up, Tiny,
okay.
which
Yeah.
is I'm looking at the printout of the paper as you go through your presentation. Do you have? I don't see any reference for this WKB expansions in terms of either a book or a paper or something like this. Would you have anything to that you could point towards?
Yes.
Or we can do this later.
Yeah, we can do it later. Yeah. This is a classical expansion, but it's most often used in sort of physics, at least initially. You can use it for doing sort of formal analysis of systems.
Okay.
Yeah.
Cool.
So
thank you.
Mathematical physics book you can probably find, but I have a reference for you. But okay. All right. So once you have this WKB expansion, we can. once you have the eigenfunction up to a multiplicative constant, you can use that to calculate the mixing time. So that's sort of just something you have to sit down and do, essentially. It's a little bit too much to put in the presentation, I would say. But we can take a little bit of a like a representative calculation, I would say, sort of like just rough. So if gamma is between 1/3 and 1, you actually only need to do the WKB expansion, essentially one step. You only need the first S1 term in the expansion. And it turns out that that gives you precisely this guy, which is basically just the integral of 1 over b prime of S ds. And that gives you sort of the leading order guy. There's a lambda k. Yeah. So if you want to calculate this coefficient, it's basically just a pointwise value of the eigenfunction around x0 when you have scaled it with the correct epsilon guy. So remember, you had this rescaling, which was like u epsilon of x was u of x epsilon to the minus 1 over 1 plus gamma. That's basically, just plug that in here and you see it's the same. It's just the 1 minus gamma comes from this part. Yeah. So if you do this and you set the tk epsilon to be this guy and you let the t epsilon be something that kind of looks like this, you can sort of read out here also the window size. Because if you choose t so that the coefficient in front and sort of these two terms are sort of the same size, then if you deviate from that correctly chosen t epsilon, then if I just cancel out the epsilon dependency in the eigenvalue, I will basically get the window from there. Does that make sense? Well, I hope so. So that's sort of what you do. And then you do this for each term in the sum. You use this pointwise estimate. You use the definition of the cutoff time using the relaxation time for gamma being bigger than 1 over 3. And then you have proven cutoff, basically. So that's sort of the point. And sort of one heuristic one can have in this situation, and this heuristic also works for the Ornstein-Uhlenbeck, is that at the cutoff time, the contribution from all the terms is roughly of the same size. So that means that the smoothing effect of the semigroup hasn't sort of yet kicked in. So after the cutoff time, the first mode will be dominating. And below the cutoff time, the last mode will be dominating, which is the most highly oscillating mode. So that's sort of one way to look at it. And if you want to see kind of what happens with the eigenfunctions when you pass this threshold. So when you go below 1 over 3, it turns out that you have the same term that exists in the bigger than 1 over 3 case, but you also get an extra term, which is not bounded. This is a lower order term, but the problem with this term is that it scales differently with respect to epsilon as the first term does. The first term scales similarly as the eigenvalue. The second one does not. And this is the reason why you have to take the largest eigenvalue in your in the cutoff space or in the truncated distance to determine the cutoff. And that is also the reason why the highest mode will then eventually dominate at the cutoff time. So that's pretty much the picture that you have in this situation. And I think actually I will stop here because I think I'm sort of running out of time. So I should leave some time for questions.
Oh, great, thank you very much. Oh, are there any questions or more questions? So when I understand correctly, this threshold of 1/3 is only meaningful if you do a cutoff, if you do a threshold, if you do a truncation. So if you truncate the metric, this 1/3 will play a role, and otherwise it would not play a role, right?
I am not so sure because it's, I mean, the shape of the eigenfunctions are different.
Yes.
So
but this
there's something happening in the eigenfunction that you get extra terms. So every when gamma is 1/k and k is an odd number, you get one more term.
Mm.
And in fact, the eigenfunctions look like this.
Mm-hmm.
So this is the kind of expansion you have. And then at precisely the 1/3, there's also like a log term that pops up.
Mm-hmm.
Yeah.
So if you wouldn't use the truncated distance, you couldn't pick the highest eigenvalue because there are infinitely many eigenvalues.
Yeah. I mean, I don't know if you can see any cutoff. I'm not sure. I don't know, but it seems to me that it's a strange question when gamma is less than 1/3 to look at the full distance. But it's certainly visible in the truncated distance that something happens with the.
Okay, any other questions?
Hello, Benny.
Yeah, hi, Michael.
I have one question. So if you look at also in this direction, what Jonas asked, if you look at the cutoff distance at the value, the eigenvalue n. So this is in some sense a weighted distance. So if you think of a weighted distance over all of them, but you have a weight and you have some just fade out of the higher values, could you think of a cutoff in this case?
You mean like
Not just taking the first one and then just set it to 0, but you have something which is also like some kind of weight for the spaces you have.
That's an interesting question. It's too bit. Well, I don't know. I have to calculate something. But do you have like some kind of example of what kind of weight you would like to look at, or in which situation this would be?
Well, of course, I think the mean of this weight, in some sense, weighted against the eigenvalues, should have some kind of meaning, I guess. I don't know. No, it's just a lucky shot. But I think just cutting off is, of course, the first natural thing to do. But maybe there's a more universal thing behind.
Yeah. Actually, now that you mention it, okay, yes. I think if you take like a weight which is summable,
Yeah, something like that.
Something like that, then it has to. Okay. This is one of the problems with our estimates, is that it's very difficult to control the coefficient in front of this in this comparison constant, how that depends on the k in this case, or n. Yeah. No, k. So sorry, this is lambda in this drawing. So as lambda gets large, you have to the constant can get very large, and we don't know how fast this goes with the size of the lambda. This is one of the reasons why we cannot take the full distance, because we cannot guarantee any summability. But if you just but it's a very good question. I mean, if you just would take a weight decaying fast enough, you would be able to use these estimates to prove cutoff in that weighted distance. Yes. Yes. Correct. Yeah. Very good. Yeah.
Thank you.
Great.